When do thermodynamic properties become critical in device failure analysis? Have you ever wondered how temperature and material changes can lead to device failures? Understanding when thermodynamic properties become critical in device failure analysis is essential for anyone involved in engineering or technology. Let's break this down into simpler terms. Thermodynamics is all about how energy changes and how materials behave under different conditions. In devices, especially electronic and mechanical ones, heat plays a big role. When a device operates close to its temperature limits, it can lead to material breakdown, phase changes, or mechanical stress. Thermodynamic properties become especially important in failure analysis when certain conditions arise. First, consider thermal stresses. These occur when materials with different coefficients of thermal expansion are joined together. If one expands more than the other during heating or cooling, it can lead to cracks or fractures. This is particularly common in solder joints in electronics. Next, think about phase transformations. These happen when materials change from one state to another, like melting or crystallizing. Such changes can weaken materials or alter their electrical properties, leading to unexpected failures. For instance, if a metal melts at a certain temperature, exceeding that temperature during operation can lead to catastrophic failure. Another critical aspect is heat accumulation. When devices generate heat but cannot dissipate it effectively, localized overheating can occur. This can cause melting, oxidation, or changes in the material structure, all of which degrade performance. Chemical reactions also play a role. High temperatures can drive reactions that produce harmful phases or corrosion products. These can compromise the structural integrity of a device, leading to failure. In practical terms, thermodynamic calculations and measurements are used to identify these critical conditions. For example, thermal analysis techniques can verify melting points and phase stability. Thermodynamic modeling can predict how materials will behave under different temperatures and conditions. In electronic devices, techniques like lock-in thermography help detect abnormal heating patterns. This can indicate faults like leakage currents or shorts, which are directly related to thermal behavior. When joining different metals, understanding thermodynamic predictions can help anticipate phase formation at interfaces. This knowledge is vital to prevent cracking and ensure reliability. In summary, thermodynamic properties become critical in device failure analysis whenever temperature changes or thermal stresses affect device reliability. By understanding these properties, analysts can better predict failure modes related to heat and material behavior. This knowledge is key to improving diagnosis and prevention strategies in real-world applications.